Welcome to the ePathshala lecture series in computer science. We are dealing with the course computer architecture. This module is on the execution of a complete instruction, the control flow. So this module is to discuss how the control flow is implemented when an instruction gets executed in a processor. And we are going to use MIPS architecture as a case study, and we will also discuss the basics of microprogrammed control. So this is the full data path of the MIPS implementation which we have already seen. So you know we have been looking at a subset of instructions of the MIPS architecture, and we have looked at the data path implementation for the subset of instructions that we are looking at. So you have an instruction fetch which is happening here. You have the instruction fetch where the PC is used to fetch the instruction, and then the register reads happen in this clock cycle, and then you have the ALU operations taking part in the third part of your instruction cycle, the memory access happening then, and then the write back happening. So having seen the data path, now we look at the various control signals that are needed. So some of the control signals have been identified here. So if you look at the control signals, you know that the control signals examples have been shown here. Say for example, you have the PC source control signal, where the PC source is used to identify which is going to be used as the data that is to be written into the PC. For example, whether it is going to be PC plus 4 or the branch address instruction. Similarly, you have an ALU source here which will tell you which either the register's contents or the sign extension is going to be used for the as one operand that is given into your ALU. So likewise, we have already defined all these control signals. Now we look at how the control path is getting implemented. So if you are looking at the ALU control here specifically for the MIPS implementation, now I would like to stress that this is going to be different for different processors. We are only looking at the MIPS architecture, and for the MIPS architecture, suppose we implement the control in such a way that you have 4 bits for the ALU control, where the various functions that get implemented are AND, OR, add, subtract, set on less than, nor we have not included NOR in our subset of instructions, but it is used for the other implementations. So if it is a load or a store instruction, you know the effective address has to be calculated. So in order to calculate the effective address, you will have to do an addition operation of the base address and the displacement component. On the other hand, if it is a branch instruction to be executed, the branch is branch if equal to or not equal to. So you have to compare the two contents of registers. So a subtraction operation has to happen there. Similarly, if you are looking at any arithmetic type of instruction or R type of instruction, it depends on the function field. Recall that you have a function field as part of your RR instruction type. So that will tell you what type of arithmetic operation is to be executed. So depending upon the function field, and if it is an R type instruction, you will have to decide whether you have to perform an AND, or addition or subtraction. Now in order to do that, what happens is, you know that the first 6 bits of your instruction, all instructions carry the opcode part. So now 2 bits of your opcode part called the ALU op are taken, and that is used along with the function field in order to decide what operation is to be executed. For example, if it is a load instruction, the ALU op part is 0 0. If it is a store instruction, it is again 0 0. For an R type instruction, it is 1 0. So if it is an R type instruction having an ALU op of 1 0 0, and if the function bits are this, then based on these two fields, you decide whether an addition is to be performed or a subtraction is to be performed, or an AND or an OR, and accordingly the ALU control signals are generated. The 4-bit ALU control signals are generated. Now to recollect the instruction formats that we have assumed for the MIPS architecture, the R type instruction, you know the R type or the load store or the branch instruction, all of them have 6-bit opcodes as you can see. The R type instruction has 3 register specifiers, 2 source registers and 1 destination register, and also a function field which I mentioned earlier. So, this function field is used in along with the ALU op bits which are part of your opcode bits to decide what ALU operation is to be executed by the processor, accordingly what control signals are to be generated. If it is a load or a store instruction, you have a source register which forms the base register, and you have a destination register for a load operation. You have the data that is available for the store instruction. The address is specified here, which is going to be used, which is going to be sign extended and is going to be used for effective address calculation. For a branch instruction, again these two registers are the registers whose data are going to be compared, and this gives you the target address which is going to be shifted left by 2 bits and it is going to be added to the program counter. So, now if you look at the data path with control, so the controls have been shown here. So, you can see the controls here. The control part has been shown here. So, you have a register destination. So, the control from the instruction is being fed here. The opcode part of the instruction is fed to your main control unit, and the control unit generates all these control signals. The register destination will tell you which register is going to be used for your destination register. So, that goes as a control for this multiplexer, whether it is going to be RT which is going to be used as the destination register or RD which is going to be used as the destination register. The branch control signal decides on the branch operation. So, this tells you whether the branch has been evaluated by true or not. The memory read instruction is going to be used for your memory data memory in order to perform a read operation. Similarly, a memory to read control signal is given to this multiplexer here, which will tell you whether the data that is read from your data memory or the data that has been output from the ALU as part of your ALU operation is to be used as your data to be written into. ALU source similarly helps you decide between the register operand that has been read here or the sign extended operand that has been read here, and register write is of course for the register here when you are performing a register write operation as part of your write back cycle. So, these are the various control signals. That is the main control which is derived based on the opcode part. Apart from that, you also have an ALU control signal unit here, a smaller control unit here, where it takes the 2 bits from your opcode part. So, you have your ALU op 2 bits from the opcode part that is given to your ALU control unit, which in turn along with the functional units, function part is decided as indicated in the table below in an earlier slide. It will decide what ALU operation is to be performed by the ALU unit. So, these are the various control signals. So, if you look at an R type of instruction, this slide shows you the flow of instructions and the various control signals that are getting generated for an R type instruction. So, as usual, an instruction fetch happens, instruction decode happens and register reads happen, and once register reads happen, the next one is the ALU operation. For the ALU operation, so you have your ALU operation, this input is given to your ALU control signal and that control signal decides what ALU operation is to be performed. And once the ALU operation is performed, a memory operation does not happen here because it is only an R type of instruction, and then the register read, register write happens or the write back happens from this multiplexer. So, the result of your ALU operation is passed on to this multiplexer and from there it is written into your register file. This is for an R type of instruction. On the other hand, if you look at a load instruction, the first part of course is common. For your ALU unit, the ALU control signals do not have significance here in the sense of an R instruction, but ALU control signal will basically tell you that an addition is to be performed here, because for a load instruction it is only an effective address calculation which is done in your ALU unit. The control signals which are significant here are the memory read control signal, because it is a load instruction that has to be generated, and once the data has been loaded from data memory, that is written back into your register file, and which register it is to be written into is also decided by means of your source register control signal here, which will tell you which register is to be written into. This is for a load instruction. If you look at a branch on equal instruction, similarly the instruction fetch is the same, decode is the same, register reads are the same. Here when you are trying to look at the equality that is going to be decided, it is only equating the two registers here. So, you have two registers which are being read, both these registers are going to be checked whether they have equal condition or not. So, that happens here, and then you have your branch instruction which is being executed. So, you have your branch happening here, the condition getting evaluated here, and once the condition gets evaluated, so you have your data being fed to your PC depending upon the branch getting satisfied or not. So, in order to calculate your branch address, you have the data being sign extended here, and that value is shifted left by 2 bits, and that is given to your adder unit that is given here, which decides on the target address, and that target address is written into your program counter. That is for your branch on equal instruction. Now, in addition to these instructions, if you are also interested in implementing jumps, this is the format of a jump instruction, where again you have a 6-bit opcode and you have a 26-bit address that is given. Now, when you are using jumps, remember that jump uses word addresses. So, this 26-bit address will have to be shifted left by 2 bits, or you have to append 00 so that it becomes a word address, and the updation of the PC happens with the concatenation of this 26 bits and the 4 bits of your old program counter with the last 2 bits 00, and a jump instruction needs an extra control signal decoded from the opcode. So, this shows the data path with jumps getting implemented. So, as you can see, you have a new jump instruction, jump control signal getting incorporated here, and the jump signal is given as one input to this multiplexer, the multiplexer's control signal. So, if this control signal is active, then this multiplexer, as you can see, it takes from data from this multiplexer, where it gives you, if the branch condition is not satisfied, it just gives you the addition of the two values PC plus 4 and the target address. So, that is given here, and if you can see here, the PC plus 4, which is your 31 to 28 to 31 bits, that is shifted left by 2 bits, that is the most significant bits. The 26 bits that you already have in your jump bits are getting added to it. The most significant 4 bits of the PC remain the same. So, all that together forms your jump address, and that is loaded into your program counter. So, the most significant 4 bits remain the same, the next 26 bits are given from the instruction, the last 2 bits are made zeros. So, that is how your jump address is calculated. Once your jump address is calculated, that is written into your program counter. So, the program counter may either get a PC plus 4, or it might get a PC plus 4 plus the target address, which plus the displacement component, which is going to happen in the case of a branch instruction. If it is a jump instruction, it is a totally new address that gets loaded into the program counter. So, now we have looked at different types of instructions for the MIPS architecture, and we have looked at the data path implementation as well as the control flow implementation for the example architecture that we looked at for a subset of the MIPS instructions. Now, what are the performance issues associated with this implementation? Now, if you look at this implementation, the MIPS implementation with a subset of instructions, you can identify the fact that the longest delay determines the clock period. If you are looking at a single cycle implementation, if you assume that all instructions get executed within one clock cycle, a single clock cycle period, then obviously the longest instruction determines the clock period. And the longest instruction from the subset of instructions that we have looked at is the load instruction, where you will have to read the instruction, that is the critical path, where you will have to read the instruction from the instruction memory, you will have to read the register file, you will have to go to the ALU for effective address calculation, you will have to access the data memory for getting the operand from memory, and then you will have to write it back into your register file. So, this is the critical path, and if you assume that the CPI value the average number of clock cycles per instruction is 1 for all these instructions, 1 long clock cycle, you can find out that the clock cycle is very long, and the overall performance of the single cycle implementation is very poor, because you may have different instructions taking different times, and if you assume that all instructions will have to be finished within 1 clock cycle, then obviously you will have to look at the lengthiest clock cycle possible, and you will not be able to accommodate a variety of instructions without having degradation in performance. That is the main drawback of your single cycle implementation. This may be acceptable for the simple instruction set that we have considered, but it is obviously not feasible for different instructions which have different types of timing requirements. For example, when you look at complicated instructions like floating point operations, that is because the clock cycle is equal to the worst case delay here, and there is no point in improving the common case. So, our fundamental assumption of making common cases fast is going to be beaten here, because you are only going to look at the worst case, and the timing has to be decided based on the worst case. So, this violates the design principle of making the common cases fast. Now, how do we overcome this problem? This problem can be overcome, and the performance can be improved by using a multi-cycle implementation and pipelining, which we will discuss a little later. Now, we have looked at a hardwired control so far, where you have a set of hardware circuits which will take in some information about the instruction, and based on that we saw how the various control signals get generated. We just looked at a sample architecture as the MIPS architecture and discussed how the MIPS architecture takes in the opcode information, it takes the instruction information, the other information from the instruction, and based on that it generates all the control signals that are required, that are to be generated at different points of your instruction execution cycle. Now, instead of going in for this type of control, processors also look at a different type of control called the microprogram control. Now, this microprogram control uses a sequence of instructions to control complex operations. It is called microprogramming or firmware. It is normally used for complex instruction set computers or CISC ISAs rather than RISC ISAs. Normally RISC ISAs make use of the hardwired control, and CISC ISAs make use of the microprogram control. It is slower, microprogram control is slower, but it is more flexible compared to hardwired control. Now, we look at some more details of this microprogram control unit. So, if you look at the microprogram control unit, you have what is called a control memory. So, this is the control memory. So, the control memory stores all the control signals. The control signals are basically stored in the form of bits, and that is available in the control memory. So, somehow you will have to address the control memory and get all the control signals. So, instead of the control signals being generated by hardware, the control signals are stored as bit configurations, as control words in your control memory. So, you will have to address the control memory using the control address register and then get out all the control signals. That will go to the control buffer register, and from there it will go to the control logic, and you have all the internal and external control signals getting generated. So, this is the general flow of a control unit organization, where the main part is the sequencing logic, where you decide how to sequence through the control memory, and based on that get your control signals. Now, we look at the implementation of a microprogram control, the basic details involved in the implementation of the microprogram control unit. Now, all your microprogram control unit does is generate a set of control signals. Now, generation of the control signals in all cases, whether you are looking at a microprogram control or you are looking at a hardwired control, all that is required is a set of control signals that need to be generated at appropriate instances. For example, in the case of a hardwired control, you know that when the PC is going to be used for fetching the instruction from memory, you will have to put out the address from the PC to the instruction memory. You will have to give a memory read control signal so that your instruction memory is read. At the next point, when you are trying to read the registers, you will have to give the appropriate control signal so that the registers are being read. So, there are certain control signals that will have to be generated at certain instances of time. Now, all that remains the same whether it is going to be hardwired control or whether it is going to be microprogram control. The difference lies in how these control signals get generated. In the case of hardwired control, you make use of gates, you make use of hard digital logic in order to generate your control signals. Whereas in the case of your microprogram control, you have control words. You can assume that each control signal is an on or an off, and you can store all these control signals as a control word in memory. So, each control signal can be represented by a bit, and you can have a control word for each micro operation. A macro operation, which say for example, it is an add instruction. A macro operation can be split up into a number of micro operations like fetching the instruction from memory, decoding it, fetching the operands from registers or immediate operands, adding the operands, storing the result in a register. All these are micro operations. So, for all these micro operations, for each of these micro operations, you can have a control word, and the control words will consist of a number of control signals which will be turned on or off depending on whether that control signal has to be generated at that point of time or not. So, in order to execute a macro instruction, all you have to do is get a sequence of control words or micro operations. Each micro operation will consist of a set of control signals that will have to be generated at that point of time. So, this is the basis of your microprogram control, and you also have to have a sequencing operation which will allow you to sequence through the set of control words, and you will have to add an address to specify the next micro instruction that is to be fetched depending upon the conditions that are to be satisfied. So, if you look at today's large microprocessors, many instructions and associated register level hardware are present in these microprocessors, and many control points will have to be manipulated. And this results in a control memory that contains a large number of words corresponding to the number of instructions to be executed, and it has a wide word width. Because you have a number of control signals, you are going to have a large word width for your control words. And due to the large number of control points to be manipulated, the word size really becomes too large. And the microprogram word length basically depends on three factors. It depends upon the maximum number of simultaneous micro operations supported. It depends on the way control information is represented or encoded, and it depends on the way in which the next micro instruction address is specified. So, as each micro operation is executed based on a control word, you will also should be able to specify where to get the next micro instruction from or the control word from. So, that is the next instruction address. So, these are the three main components which decide on your three factors which decide on the length of your control words. So, based on these, based on the encoding that is done, you have two types of micro instructions. One is called vertical microprogramming and the other one is called horizontal microprogramming. So, in the case of vertical microprogramming, each micro instruction specifies single or few micro operations to be performed. You have a large amount of encoding that is done. So, the word length basically reduces, but you may have to do multiple levels of decoding. So, you do not have too many micro operations which are specified in parallel. On the other hand, when you go in for horizontal microprogramming, the word length becomes very large and you have many different micro operations to be specified in parallel. So, in the case of vertical microprogramming, the width is narrow. You can have n control signals which can be encoded into log n to the base 2 bits. So, you have limited reduced number of bits because it is encoded. Because of that, there is limited ability to express parallelism. Considerable encoding of control information requires the external memory word decoder to identify the exact control line being manipulated. Because the control signals are not available directly, you will have to decode it first of all, and only the decoded information will give you the various control signals to be generated. On the other hand, if you look at horizontal microprogramming, it has a wide memory word, there is high degree of parallel operations possible, and there is only very little encoding of control information. This gives you an idea of these two formats. So, if you look at a horizontal micro instruction, see the last field indicates the micro instruction address, which is common to both types of formats. That will tell you what is the next micro instruction address. Say I have a jump condition here. Suppose if you have a jump condition that is indicated here, and all your other bits are given here, whether it is based on unconditional jump or a 0 condition or overflow or an indirect bit, whatever it is. The system bus control signals are given here, for example, and the internal CPU control signals are given here. So, you find that many of these operations are specified as separate fields, and there is a large amount of parallelism available here. The control signals are explicitly specified. Whereas, when you go in for a vertical format, the jump condition is given here, but all these conditions that are possible for your jump instruction are encoded into a particular field, and it is given as function codes. So, you do not have the control signals being available directly here. These function codes will have to be further decoded for you to generate the control signals directly. Now, this is normally we go in for a compromise between vertical microprogramming and horizontal microprogramming, where we divide the control signals into disjoint groups and implement each group as separate field in a memory word, and this supports reasonable levels of parallelism without too much of complexity. Because you can't go in for a purely horizontal microprogram control or a purely vertical microprogram control. A minimal level of encoding is definitely required. So, we will have to go in for a compromise. Another thing which you will have to look at is there are many common parts that are going to be executed in each and every microprogram sequence. So, for example, if you are looking at the fetch sequence, the fetch sequence is going to be the same for all instructions. So, are you going to have the fetch sequence included as part of each and every microprogram, or is it going to be available in a common place? So, you will have to decide on all that. So, you have micro routines available for the various operations. The common routines are available in one place. The sequencing control will make sure that it sequences through the proper set of micro instructions or control words in order to execute the particular macro operation. So, again, to look at the control unit, having discussed the basics of microprogram control. So, you have a sequencing logic which will allow you to sequence through the control memory and generates the next micro instructions address that goes to the control address register, which is used to address your control memory. The words from your control memory, which is your control word, is put into your control buffer register, from where you have all the control signals getting generated. If you look at vertical microprogramming, the words that are got from your control register may have to be decoded to one or more levels in order for you to generate all the control signals. So, if you look at the control unit function, it has to sequence it has a sequence unit which will issue the read command. The word specified in the control address register is read into the control buffer register, and the control buffer register contents generates the control signals and the next address information. The sequence login loads new address into the control buffer register based on the next address information from the control buffer register and the ALU flags. Now, next address decision may be dependent upon the jump instruction, or it may be just a next instruction. So, you just have to add 1 to the control address register, or based on certain conditions getting evaluated. If it is a conditional jump instruction, based on that you will have to do a jump operation. So, this is the complete functioning of your microprogram control. So, based on the flags and all that, your ALU flags, your sequencing logic decides which instruction is to be executed next. That is given here to the control address register. Your control memory is addressed, you have the control words, and the control words may have to be decoded, and you have all the control signals getting generated. So, if you look at the advantages and disadvantages of microprogram control, microprogram control simplifies the design of the control unit. It is cheaper and it is less error prone, but it is obviously slower compared to your hardwired control. So, tasks done by the microprogram control are basically micro instruction sequencing, execution, and obviously you will have to consider both together to get an optimized design. So, the design considerations are the size of the micro instructions and the address generation time, which is determined by the instruction register, the next sequential address, and depending on whether you have branches or not. So, these are the sequencing techniques will depend upon the current microinstruction, the condition flags, the contents of the instruction register, and accordingly the control memory address must be generated. And you may have different formats of address instructions here, 2 address field, single address field and a variable field. So, this is the encoding and decoding that we discussed. So, if it is direct and encoding, you have the control signals directly available. If it is indirect encoding or vertical microprogram, you may have to have multiple levels of decoding. So, this is the control unit implementation for both. You have the hardwired control shown here, where a set of logic gates decide the control signals, whereas here the control memory is responsible for generating the control signals. So, in order to summarize, we have looked at the control flow for the MIPS architecture. We have seen the generation of the various control signals for a sample MIPS architecture, which is generated depending upon the instruction, and we also pointed out the drawbacks of the single cycle implementation. The next part, we looked at the second type of control that is possible in processors, which is called the microprogram control, where we looked at the basics of microprogram control, some details about its implementation, and we had a comparison with hardwired control. Thank you.